All right, so section 10 is on differentiability and the power rule. So we talked a little bit about differentiability last time. And we said that things are not differentiable if we have a corner or a cusp. So an example of that would be like y equals the absolute value of x. And when we talked about this, we said that the slope on the right side was 1 and the slope on the left side was -1, which you can kind of count. This is not absolute value of, oh yeah, it is. It's just weird units. So we say that the slope on the right is 1 and the slope on the left is 1, but the slope actually at 0 is nothing. Okay, we would need the slopes on both the right and left to go towards the same value. Okay, so since it's very pointy like that, the slope at 0 is undefined. So the same is true for something like a cusp. You can tell on this cusp that the slope on the right side is positive, the slope on the left side is negative. So the slope you would think is going to approach 0, but it doesn't. It doesn't like flatten out and become a slope of 0, like a horizontal tangent line. It's very, very pointy. So that's called a cusp. So right here, the slope is undefined. All right, sometimes you might have a vertical tangent. So an example of that would be like h of x equals x to the 1/3, or you might see that written as the cube root of x. So if you have the cube root of x, momentarily, for the briefest of moments, you have a vertical tangent line. Okay, the slope is perfectly vertical. So the slope is what we would call undefined, right? A vertical line has an undefined slope. And then a discontinuity, this is the Heaviside function. We did one before that was the signum function, which was 1 and -1. But the Heaviside function is 1 and 0. So yes, I agree that the slope here is 0, and I agree that the slope here is 0, right? So the slopes on the left and the right are the same. So you would think that the slope at the place where they're meeting is going to be 0 as well, but it's actually not. There's a discontinuity there. So we don't say that the slope at 0 is 0, we say that the slope is undefined. So even if there is a point there, right, you guys agree there's a point there, but there is no slope at that point. So even if you have something like some kind of curve like this, there's no slope right there. There's nothing on the right of it. Okay, so it's kind of confusing. So at any discontinuity, there is no, the derivative is undefined. All right, so number 1, yes?
Wait, so there's no slope at that point at 0, so...
Yep, so the slope is undefined.
Because there's nothing coming from the sides.
Yeah, it's because there's a discontinuity, basically. And so even if you had like a graph that looks like this, yeah, you can tell that the slope is equal to 0 here, the slope is equal to 0 here, but since that point is not even existent, it's not even there, then we say that there is no slope at that point. Okay, so it's really weird because it's like, but the left-hand derivative is the same as the right-hand derivative, it should work, but it's not continuous there. All right, so number 1, so find all points in the domain where f is not differentiable. So if you guys know your transformations, this is what we're doing in pre-calc right now, transformations, you should know what this graph looks like. Can you see how much it's been shifted? Right, left, up, down. So where does it go? Up 5 and right 3. 1, 2, 3, 4, 5. Otherwise, everything looks exactly like y equals absolute value of x, right? The slope is still 1 and -1 on each side. So where is it not differentiable? Yeah, so we would say at x equals 3. So you don't have to say at the point, you just say not differentiable at the certain x item. So right there at the corner. All right, if you weren't sure what the transformations did, if you've forgotten all of that, you could always do a t-table, right? So you could try a t-table to figure out where it is. All right, so there's something on your calculator that will compute derivatives at certain numbers for you, okay? I caution about using this, and it's kind of weird that I'm teaching this before I even teach you how to do the shortcut. But I've told you before that there's 2 parts to the exam. There's a calculator portion and a non-calculator portion. Guys, stop talking. So if you are on the non-calculator portion, or if you're on the calculator portion and you're trying to figure out a derivative and you're like, oh my gosh, my function is crazy. It is like the square root of e to the x sine of x all over x squared. I don't even know how to take the derivative of this. I have no idea. But it wants the derivative at 2, right? then you could actually do that. You could do the derivative at a certain x value on your calculator, okay? So here's the thing. So in this first example, it says compute the derivative of f of x equals x cubed at x equals 2 by hand, and then by the numerical derivative function. Okay, so if I'm computing the derivative by hand, that's the thing, right? I haven't taught you the shortcut yet, where we do limit as h goes to 0 of x plus h cubed minus x cubed all over h. And we would FOIL it all out, so we'd have the limit as h goes to 0 of x cubed plus 3x squared h plus 3x h cubed, no, h squared plus h cubed minus x cubed all over h. We'd cancel some stuff, dot, 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 and we would get the answer of 3x squared. So you can finish that out if you want, but you'll get 3x squared. Just 3x squared, because the h will go to 0. All right, so if I'm finding f prime of 2, then it's going to be 3 times 2 squared. So we end up getting 12. Okay, so I know my derivative, my slope at x equals 2 is 12. All right. Now what the numerical derivative function does is it does a very numeric answer, right? It finds this on your calculator. So it basically zooms in to a certain point. So in our case at x equals 2, and it finds really, really close to 2 on both the right and left and finds the slope between those 2 points. So it goes to 2.001 and not negative, 1.999, and it finds the slope between those 2 points. Does that make sense? So let's figure out how to do that. So go ahead and on your calculator, so everybody get your calculator out. So you're going to hit Math 8. And you might have this come up and it might say end deriv. So I'll write both setups. So on this calculator, it comes up as d over d blank, and then parentheses with a blank, and then a line with blank blank, right? There's lots of stuff. So here's what we put in. We do d dx of x to the 3. Oops. I'm still in parametric mode. That's not good. So mode, function. Sorry. Let me go back. So Math 8. All right. So d dx of x to the 3. And then we're evaluating at an x value of 2. All right. So let me write what I just did. So I did d dx of x cubed evaluated at a certain x value at x equals 2. Now, if you did not have that come up and it says end deriv, how many of you guys have end deriv? Yeah, a couple of you guys. It's going to look like end deriv of the function x cubed. The derivative is taken in terms of x. Oops. I don't know what's going on here. At x equals 2. So you would put it in with commas. So either way, when you guys do this, so I hit enter. See how I got 12.00001. How many zeros did I have? 5. So I get 12.1234551. All right. It did not give the exact answer, yes. Okay, it's the end deriv thing, this. I just wrote it. So I'll say end deriv, x cubed, comma. All right, so it doesn't actually give you the right answer. And most of the time, end deriv does not give you the exact right answer. That's what's frustrating about it. Sometimes it will, but a lot of times it's going to give you something that's super, super close to the answer, but not exactly it. Okay, so what I would say is only use it, for the most part, as a last resort. Okay, so I'll teach you some, when we review before the test in May, I'll teach you some shortcuts and so on, and when you would want to use this. But for the most part, try to do it by hand, and if you can't, use end deriv. Okay? All right, so let's come up with the formulas. So there's a shortcut. Let's figure out what these are. So let's do it the long way first. So this table right here, so Chloe's table, I want you to find number 1. I want you to do the long way. So you're going to say the limit as h goes to 0 of f of x plus h minus f of x all over h. In table 2, so Alex's table, I want you guys to do number 2. Table 3, you guys back there, I want you to do number 3, and then table 4, you do number 4. And I'll do them as you guys are doing them. I did it super speedily. Don't look at mine. Try it on your own.
I know that's not going to be done.
Yes. Okay, did you guys get 0 for the first one? What'd you get for the second? Yep. The third one, what'd you guys get? 2x, yep. Good, so you guys are getting the same thing? Good. And the last one? Yep, 3x squared. Good. So there has to be some kind of pattern to this. So let's think about it. So this first one was c, which is the same as c x to the 0. Right, there was no x value. The next one was x, which is the same as x to the 1. Jack thinks he knows it. The next one is x squared, and the last one is x cubed. So Jack, what do you think the pattern is?
I think you bring the power of the x value out front and reduce the original power by 1.
That is exactly the pattern. Okay, so you're going to bring the power that you had, you're going to bring it to the front, and then whatever power you had before, you're now going to subtract 1 from it. So see how you have x cubed? You're going to take the 3 to the front, and then you're going to do x to the 2. Okay, so this one was 2, and then it's going to be x to the 1. This one was 0 times c, so 0, and then it's like x to the negative 1, which doesn't matter, so we still get 0. And this one's 1, x to the 0, which is just going to be 1. Okay, do you guys see the pattern? All right, so we call that the power rule. So if you have just a constant, so if you have just c, so the derivative of like 5, the derivative of 7, the derivative of 10, right, its derivative is always going to be 0. All right, and it makes sense if you think about what the graph looks like. So if I had y equals 10, what is the slope of that line? It's 0, right? That's what we're saying. What's the derivative? What's the slope of the line? 0. But if I have something like x to the n, its derivative is going to be what? So we said the power goes to the front, so n, and then x to the n minus 1, right? So if I had y equals x to the 6th, its derivative will be y prime equals 6 x to the 5th. So you bring the power to the front and you subtract 1 from the power. All right, now derivatives have to do with limits, right? We did the whole long limit definition. So any limit rule that you have will also apply to these. So if I have the derivative of a constant times f of x, the constant you can actually pull in front of a limit. So it's going to be the constant times the derivative of f of x. Okay. I don't like writing the derivative d over dx of f of x. So a lot of times I shortcut it. How do I write a derivative of f of x? F prime, right? So I'm going to write c times f prime of x. So a constant you can pull out. Actual functions you can't pull out. Like if it had been f of x times g of x, you can't just like, oh, I'm just going to pull f of x to the front. It doesn't matter, right? All right, but if you have the sum, then you take the derivative of each thing. So this is going to be f prime of x plus g prime of x And this will be f prime of x minus g prime of x. So you just take the derivative of each individual part. So basically, if you have a big long function and you have x to the fifth minus 3x to the fourth plus 7x minus 2, you just take the derivative of each individual portion. So its derivative would be 5x to the fourth minus 12x to the third plus 7 and then plus 0, right? I did it very speedily. Do you see how I got that? So 4 times 3 gives me 12. Subtract 1 from the power. This was 7x to the, not 0, to the 1. So 1 times 7 is 7. X to the 0 is just 1. Yep.
Taking like the second derivative, just be doing that again.
Yep, it would be doing it again. So if you have the second derivative, you would go again. So the first derivative tells you about the slope. The second derivative tells us about something else. It's called concavity. So we'll talk about concavity later. All right, so why does this work? So the proof of the constant multiple rule, I mean, you could do the proofs of each of these rules and see why it works. But basically, if we have g of x is equal to c times f of x, if I want to find g prime of x, I would do the limit as h goes to 0 of g of x plus h minus g of x all over h. So I'd have the limit as h goes to 0 of g of x plus h is the same as c times f of x plus h minus c times f of x all over h. And you can pull that c, right? You can factor it here. So you're going to have f of x plus h minus f of x all over h. And once you pull it to the front, you can actually pull it all the way in front of the limit. So I'm going to pull it out there. So you get c times the limit as h goes to 0 of f of x plus h. So what is the limit as h goes to 0 of f of x plus h minus f of x all over h? What's this portion right here? What do we call that? It's f prime of x, right? It's the derivative of f of x. So it's going to be c times f prime of x. So we proved it. So that's the proof of the constant multiple rule. So you can pull a constant out and then just take the derivative of what remains. Okay, so number 1, so I have f of x equals 5. Okay, it's a constant. Think about y equals 5. What's the slope of a line y equals 5? It's 0, right? So f prime of x is equal to 0. So if you need to rewrite it so that it's 5x to the 0, you can. So 0 times 5 is 0. And then the x part doesn't matter then. All right, so as you're getting used to the derivative, you want to do one thing at a time. So if I have 2, and then I have x to the 9th, what is the derivative of x to the 9th? 9x to the 8th, right? And then plus, what's the derivative of 7? 0. So you end up getting 18x to the 8th. But most of you guys can see that you don't have to do it like in pieces like that. Like really what you're doing is you're taking that 9 and you're multiplying by the 2. That's how you're getting the 18. Does that make sense? You don't have to like break it apart into steps. All right, so this next one, we're going to have f prime of x equals, what do you think? Who wants to go for it? Yeah, Jack.
Negative 15 x to the fourth plus 40x cubed plus 4x to the negative 1.
Ah, very close, but not negative 1. Negative 3, subtract 1 from the power. Tricky, tricky. Yep, so negative 15x to the fourth plus 40x to the 3 plus 4x to the negative 3. So he's just bringing every power to the front and multiplying, and then he's subtracting 1 from each power. See how easy this rule is? Okay. Can you imagine doing it with the limit as x goes to h business? Think about x to the 5th. You'd have x plus h raised to the 5th. Oh man, aren't you glad I taught you this shortcut? I could have tortured you for days. All right, so this next one. This one is kind of hard still, because now we have y equals 3x minus 2 cubed. We actually do have to multiply it out. So we're going to multiply it out before we can take the derivative. Right now, there is something we learn later called the chain rule. All right, so I'm going to have y equals, and I'm going to multiply 3x minus 2 times itself 3 times. You could also do your binomial theorem, 1, 3, 3, 1. Right, you could do all that. Doesn't take long though. So 9x squared minus 12x plus 4 times 3x minus 2 So 27x cubed minus 18x squared minus 36x squared plus 24x plus 12x minus 8. So we get 27x cubed minus 54. So 54x squared plus 36x minus 8. So that means its derivative is what? Yep, Jay. That is exactly right. Good. 81x squared plus or minus 108x plus 36. So you're just taking the power, multiplying by the number out front. So 27 times 3 is 81. 54 times 2 is 108, and so on. All right, now, you know, math builds on itself. There's a whole reason you had like algebra 2 first and then pre-calc and so on. So when you see something like this, f of x equals the cube root of x to the fifth, you know what power that is actually raised to. Okay, so we need to first rewrite it. So we have f of x equals x to the 5 over 3, right? It's power over root. So the power was 5, the root was 3. Plus 4 times x to the 1/2, right? A square root is a 1/2 power. So you first need to rewrite it so you can see what your powers are. So now when we take the derivative, we get f prime of x equals, so we're going to pull the power to the front. So we're going to have 5 over 3 x, and it's a little tricky. We have 5/3 minus 1. 5/3 minus 1 is 5/3 minus 3/3. 2/3. Plus 4 times 1/2, 2, x to the negative 1/2. Good. 1/2 minus 1 is negative 1/2. Okay, do you need to get that? Yep. All right, and then this one is the same idea. You cannot just take the derivative of the numerator and the derivative of the denominator. It does not work that way. Okay? You have to rewrite it so that you have x to a power, x to a power, x to a power. Okay, so what we're going to do is we're going to bring the 2x into both pieces. So we're going to rewrite, so we have g of x equals, it's x to the fifth over 2x minus 3x squared over 2x. So it's really x to the fourth all over 2. So instead of writing x to the fourth all over 2, I want to see what coefficient is out front, like what number is out front. So I actually write that as 1/2 x to the fourth. Does that make sense? So you're pulling the 1/2 out. So I'm going to have 1/2 x to the fourth, and then minus what? 3 over 2 times x, right? So that's g of x. So we still haven't taken the derivative yet, though. Don't get confused. A lot of people just do the simplification, and they're like, oh, I'm done, and they forget the derivative part. All right, so g prime of x is equal to 4 times 1/2 becomes 2, x to the 3 minus, what's the derivative of 3 over 2x? 3 over 2. Just 3 over 2, right? So that's our answer. Okay, is this making sense? Okay. A couple more hard ones. Whoops. So this one. So I have the cube root of x times x cubed minus 5x squared all over 3x. So slowly simplify all the way down, right? So let's multiply across the top first. So I have the cube root of x, that's x to the 1/3. And I'm going to multiply it n. So I'm going to have x to the, I have 3 plus a 1/3. So if you need to write that off to the side, go ahead and do it. 3 plus 1/3 is 9 over 3 plus 1/3. So we get 10/3 minus 5, and we have 1/3 plus 2, right? We're adding our exponents. So we're going to get 6 over 3 plus 1/3 is 7/3, all over 3x. So when we divide that 3x into both pieces, we get 1/3 x to the, we had x to the 10/3, and we're subtracting out x to the, like the 1. 10/3 minus 1 is 7/3, minus 5 over 3, x to the 7/3 minus 1 is 4/3. Lots of fractions. It's hard to do calculus without knowing fractions. Pretty important. All right, so g prime of x becomes So we're going to have 1/3 times the 7/3. So 1/3 times 7/3. So what do we get? 7/9, x to the 7/3 minus 1, 4/3, yep, minus 5/3 times 4/3, 20/9, x to the 4/3 minus 1, 1/3, good. So I know some of you guys have trouble with the fractions. You'll do this a lot. You'll get better, but take it very slowly. And so you see how I wrote things off to the side. If you need to do that, that's fine. Okay, you'll get good at this. You won't have to do that eventually. But all right, do you guys want to try number 8 really quickly? So go ahead and try it on your own. See if you can get it. All right, so a lot of you guys got it as I was walking around. All right, here we go. So if I do x under a 4th root, then it's going to be x to the 1/4. Oops, shh, guys. So x to the 1/4 times 6x to the 3/2 plus 2x squared all over 4x squared. Guys, so I'm going to have 6x to the, I add my 1/4 plus my 3/2. So the 3/2 becomes 6/4, so I get 7/4. All right, and then I have plus 2x to the, I have 1/4 plus 2, so that's 8/4, so I get 9/4, right, all over 4x squared. So the 4x squared goes into both pieces. So I get 6/4, so I get 3/2, and then I have x to the 7/4 all over x squared. So think about 7/4 minus 2, so minus 8/4. So I get x to the negative 1/4. Then I have plus 1/2 x to the 9/4 minus 2 becomes 1/4. Okay, did everybody get that for f of x simplified? Okay. So f prime of x then becomes 3/2 times negative 1/8, which is negative 3/8, x to the negative 1/4 minus 1. Be careful. Negative 1/4 minus 1 is negative 5/4 plus 1/8 x to the negative 3/4. Okay, so how many of you guys got it completely right? That's good. Yeah, several of you guys did. All right. So the next one says find the points on the curve y equals x to the 4th minus 6x squared plus 4 where the tangent line is horizontal. Whenever you see that, tangent line is horizontal, it's usually asking for where the maximums and minimums are. Think about that. If you have some kind of curve and your slope is horizontal, right, your slope is equal to 0, right? See how it's happening at the top and the tops and bottoms? There might be things like y equals x cubed, right, where it flattens out for a second and then goes back. But for the most part, you're asking where you have maximums and minimums a lot of times. All right, so we want to find where the slope is equal to 0. So what we're going to do is we're going to find y prime. So we get 4x cubed minus 12x, and we want that to equal 0. So we get 4x cubed minus 12x equals 0. And we can solve by pulling out the GCF of 4x. So we have x squared minus 3. And then setting each piece equal to 0. So I have 4x equals 0. I have x squared minus 3 equals 0. So I get x equals 0, and I get x squared equals 3. So x equals plus or minus the square root of 3. So there's 3 locations. But be really careful, because if the AP test says find all of the points, then you need to find it listed as a point. You just can't say add x equals whatever. Right, so we need the 3 points. So we have 0 comma something, we have root 3 comma something, and we have negative root 3 comma something. Okay. So we're going to plug in those numbers. So when I plug in 0 to the original, right, I get 0 to the 4th minus 6 times 0 squared plus 4. So do you guys see how we get 4? That one's an easy one. 0 comma 4. All right, but then what about root 3? Then we have y equals root 3 raised to the 4th minus 6 times root 3 squared plus 4. Can someone tell me what root 3 to the 4th is?
27.
Ah, close. 9. Yep, it's 9, because it's going to be root 3. Think of root 3 squared. That's going to be 3, and then you're going to square it again. So you'll get 9. Minus 6 times 3 plus 4. You're really going for that bonus point, aren't you?
I need it.
No, you do not.
Well, I want it.
So 9 minus 18 plus 4. So 13 minus 18 is negative 5. So we get -5. Will we get the same thing if you plug in -3? Or negative root 3, I mean?
Yeah.
Yeah, because to the fourth and to the second, it's the exact same thing, right? So we're also going to get -5. Okay, those are our 3 points. So there's something interesting happening at those 3 points. I think this is a W curve. So if that's a W curve, those would be those 3 points. Right, because it's an x fourth minus an x squared. All right.